Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 12, and this problem tells us that we have compound A and B. Compound A gives us two H&MR signals, one at 2.64 ppm, one at 3.69 ppm, and we get a 2 to 3 ratio for these peaks, while compound B gives us a 2.09 ppm and a 4.27 ppm chemical shift value with 3 to 2 proton ratio. So it tells us which of these two following structures correspond to compound A and compound B respectively. So what we need to do is we identify a few different things. So these chemical shift values are pretty similar to one another. We have a more shielded set of protons and a more de-shielded set of protons. But what really differs is the number of protons that correspond to each chemical shift value. So for the top one, we have two protons that are going to be more shielded and three protons are going to be less shielded or more de-shielded. So we obviously know that we have more than 5 protons in each of these molecules. So let's determine the number of unique chemical protons we have in each of these molecules. So because both these molecules are achiral, we have internal plane of symmetry between them. So we can draw that internal plane of symmetry within them. Now remember, what happens to the right side will happen to the left side. So if we fill in our protons here, we see that it becomes very clear to us that on the right side, we have two unique chemical protons, one being these terminal methyl groups that's directly bound to the oxygen, and one being these CH2 bonds that's bounded to a carbonyl carbon and another CH2. Remember, what happens to the left happens to the right, so we have these two protons are the same as these two across the internal plane symmetry, and these three protons are the same as these three. So we have a ratio, we have a total of 6, 9, 10. We have a total of 10 protons. So if I were to multiply this ratio by 2, you would have a 4 to 6 proton ratio, and we indeed do have some sort of 6 to 4 ratio. But when you can determine if this is compound A or B, well, before we do that, let's determine this molecule here. And once again, it's very clear that we have two unique proton types as well here. So now, how do we tell which one is going to be more downfield shifted? So how do we know which one of these are going to be more downfield shifted? And whichever one is going to be more downfield shifted, there has to be two conditions. Those downfield shifted protons must only equal 4 protons, while these upfield must be 6. But in this one, it's opposite. These downfield shifted protons equal to 6 protons, while these upfield protons equal to 4. Well, let's look at the integrity of, well, let's start with B. So we want to find something with 4 protons that's most downfield shifted. Well, let's look at the left molecule. So we have 4 protons here. These are chemically unique protons. However, they're all identical to each other, but they're chemically unique from these 6 protons around them. And we know that this carbon that has these 2 protons is directly bounded to a carbonyl carbon and another carbon center. Same with this on the left. We have a carbonyl carbon directly bound and a carbon center. So yes, we do indeed have 2 carbons directly bound to it, but one of them is a carbonyl carbon, so there is some sort of electron density pulling effect that can de-shield these protons to some extent. So now let's look at these 2 protons. So we have this proton, these 2 protons are bounded to a carbon that's directly bounded to an electronegative atom here. And these 2 protons directly bound to electronegative atom here. So remember, your protons that are directly bounded to electronegative atom will be more downfield shifted. Or another way of saying this is that the closer your protons are to an electronegative atom, the more downfield shifted they are going to be. So these on the left had an entire carbon between these electronegative oxygen atoms, but these protons here are directly bounded to the oxygen atoms. So it's very obvious that these are closer to the electronegative atoms. Therefore, these will be more downfield shifted, meaning they have a greater ppm value than 3. So this would clearly indicate that these 4 protons correspond to compound B's 4 downfield shifted proton. And then obviously we know that, yes, these 4 protons on the right molecule will also be d-shielded, but to a lesser extent because there's that carbon spacer. So we know that the left molecule must by default be A, and the second molecule must be B. And we can also confirm this again because now these 6 shielded protons on compound A, they're directly bounded to an electronegative oxygen atom here. But on compound B, they're bounded to a carbon. So we'd expect the 6 protons on compound A to be more downfield shifted than the 6 protons on compound B. So that means that we expect the chemical shift values of these 6 protons to be greater than compound B. And that is exactly what we see here. We have almost a 0.6 or a 0.55 greater difference in A than B, and that's due to the direct bounding to this electronegative oxygen atom. So this just confirms what we already know by looking at these 4 protons in the middle.